Okay, so in our notes, this is starting section 2.7, which is covering equations and inequalities involving absolute. Let's talk about some background information that you should have remembered from pre-algebra or algebra. Earlier in the year, we did work with a couple of absolute value problems, but it was just working with numbers in general. What do you guys remember about the term absolute value and what it means when in relation to like a number line? Yes, sir. Perfect. Hayden said it. So fill this in. It's the distance between the number and 0. Now, in this class, you're going to hear me refer a lot to the word units. I'm going to say units instead of an actual number. So, for example, if I give you the absolute value of 4, okay, or the absolute value of -4, both the answers to these two right here is going to equal to a positive version, okay, because this is saying 4 units away from 0, and even though this is -4, when we take the absolute value bars away and we translate it mathematically, it's still positive 4 units, or 4 units away. So what that would look like on the graph is 4 units in the positive direction, 4 units in the negative direction. Okay, so just keep that in mind. When I talk about units, I'm referring to using the number line. Okay. Additional information, just absolute values indicated with these bars. A lot of the stuff that I've done is handwritten, so please don't confuse that with the number 1. Typically, I try to extend them farther than the number. But with any absolute value signs, you always have a beginning and an end. So try not to let that confuse you if that's a 1 or not. Most likely it's going to be a starting and an ending point, and then what's in between the bars is what we'll be working with. Okay? Now, what's unique about absolute value? One thing that we can keep consistent is our solution, our answer. If you're working with just a number, whether it be positive or negative, will always be what? What are these two values? They're always positive. Okay, so that's something to keep in mind, that the absolute value of any number is going to be positive. Now, that's a pretty easy concept to remember. We're going to start to introduce the variables, which is going to change this theory. It's not changing it so much, but it's going to be changing the process of how we solve for it. It's not just going to be changing the numbers inside, but we're going to be working, and I'm going to show you some techniques to actually solve for x when it's inside the bars. Okay, so if you go over to page 2, these are just some properties of absolute values that you guys have either already covered in pre-algebra or regular algebra, and just some things to think about. Imagine A, that's not a 9, that's an A, as any real number, okay? Regardless of the value of A, whether it's positive or negative, the answer is always going to be greater than or equal to 0. It's always going to be a positive term, okay, like we said on the last page. Some more principles or properties. This right here represents a multiplication sign. If you'll just make note on your notes so that you don't assume that that's a variable x. What this is saying that is if we have two real numbers, a and b, and we multiply them together, regardless if they're positive or negative, if they're inside the absolute value bars, it would be the same thing as saying the absolute value of A times the absolute value of B. These are the same thing, so you can kind of rearrange and work with your real numbers depending on the situation that you have. Now these two we probably won't see a lot in the class. This last one is where we're going to start adapting to putting variables in our absolute value. So make a note that this U is representing a variable. Now, your variable can be any letter. It can be X, it can be Y, it can be S, T, it can be any symbol pretty much. So the absolute value of any variable, okay, and it's going to be equal to some real number, is the same as taking the absolute value bars away and setting that variable equal to the positive and negative version of your real number. Okay, this right here represents a real number. Okay, so let's try to apply that to solving an actual equation when we have a variable. Okay, the first one is very, very simple. It says solve for x when you have the absolute value of x equals 6. So one thing that we can take from this property that we looked at above is that this can be rewritten without the bars as x is equal to the positive version of 6 and x is equal to the negative version of 6. With all of your absolute value equations, you're going to have, unless we're talking about a special case, 2 solutions. Okay? The confusing part is that typically we are not having to deal with absolute values. So we've got to think of what values inside the absolute value would give me a positive 6. Well, 6 or negative 6. Okay? Now, you won't be graphing equations. I just put the number line on here to remind you that it's 6 units away from 0 this way. That's where you get the positive version. And it's 6 units in the negative direction. Okay? Last thing for this page, how would I write my 2 solutions? Remember, for equations, we use bracket notation, right? Since there's 2 solutions here, we are going to put it in numerical order. We're going to open our bracket first. Negative 6, we're going to separate those with a comma. Positive 6, close brackets. Now, one of the mistakes that students make in this section is they assume that the answers are always going to be the same, but a positive and negative version. That's not always true when you're dealing with absolute. For this type of problem, when x is the only thing inside your absolute value bars, yeah, it's the positive and negative version. But when we start introducing numerical factors in there, you may not have the same 2 values. Okay? So let's go on to the next page. Now, these next 2 examples, we're going to use the same theory that we just got done with the x and negative, or x and positive and negative 6. However, if you'll notice that what's different about this type of equation, it's not just a single variable, right? Inside the absolute value, there's an additional numerical factor. So you kind of have to think of this in just a little bit different than literally just substituting positive and negative versions. What we're trying to say is the values of m minus 3, what values for m can we put into that equation that would give me 4? Okay? So what we're trying to do is we want to set m minus 3 equal to the positive version of 4 as well as the negative version of 4. Because essentially if this is what's equal to either 4 or negative 4, the absolute value of that will give me the positive version. So here you're going to write 2 equations. Okay? You're going to take the absolute value bars away. You're going to write one version equal to the positive version of 4. You're going to write the second equation equal to the negative version of 4. The key thing is do not change the sign inside the absolute value. You want to keep that entire expression the same. The only thing you're changing is the number outside. Okay? And then you're just going to solve straight down at this point. Okay? How would I solve for m on this left side equation if it were by itself? How do you get m by itself? Add 3 to both sides, right? What's easy about this is typically what you do to this left side, you're going to be doing to the right one as well. Okay, and so what does my m equal? Well, 4 plus 3 is 7. The second part, negative 4 plus 3 is negative 1. So here I've got two solutions. You will write your answer in bracket notation. Make sure that it's numerically in order. So even though we solved for negative 1 on the right side over here, we do want to put that first in our bracket notation. Now I'm not going to do this on every single problem, but I do want to show how that you can hand check your answers, because remember, on portions of this class you can't use a calculator. So let's double check to see if we even have the right answers for these. Okay, let's do the 7 first. What you're going to do is plug this m equals 7 back into the original equation. So 7 minus 3 in the absolute values equals positive 4. And what you're going to do is simplify this straight down. What is 7 minus 3? 4, right? Okay, does the absolute value of 4 equal positive 4? Is that a true statement? Yeah, so that one's good. Let's do the same thing for negative 1. I'm going to plug negative 1 into my original equation and then simplify it straight down. What is negative 1 minus 3? Negative 4. Does the absolute value of negative 4 equal positive 4? Is that a true statement? Yeah. So if you get the answers to both of those correctly and those match your solution, then you know that you've hand checked it correctly. You have the right answers. Okay. Now I'm not going to hand check those all the time, but I do want to show you at least one example so you can have a resource for your quiz and test to be able to check without having your calculator. Okay, so what I want you to do is I want you to solve example number 3 on your own. If you'll notice, the format of these is identical. We've just changed numbers. Same thing is you have a coefficient in front of your x term. When you write your two equations, solve it as if it were an equation by itself. So I kind of put in on the side over here a note. If you'll look at this, in examples 1 through 3, we just got done working number 3, the absolute value portion was already isolated, meaning our equation here had the absolute value bars on one side and it was equal to some number. Looking over at example 4, I kind of made a little note for you guys. If your absolute value portion is not isolated, okay, if that's not the only thing on one side, and it contains a numerical factor outside of the bars, meaning if you look at the example 4, it's outside of the bars, you must isolate the absolute portion first before you separate and create your two equations. Okay, so let's look at example 4 real quick. Principally, we're going to be doing the same thing once we isolate our absolute value bars. So if I want to get this portion right here by itself, how do I get rid of the negative 3 that's on the left side? You add it. So the same, you're not changing any kind of equation process of moving your variables left and right. I'm going to rewrite this as 2x plus 5, and it's still in the absolute value bars. That's one of the mistakes that students make, is they drop the bars too soon. This is equal to 8 plus 3 is 11. Now from here, my absolute value is isolated. Now I can create my two separate equations. Remember, we're going to look at the inside portion needs to be 11 or negative 11. So I'm going to set 2x plus 5 equal to positive 11 and 2x plus 5 equal to negative 11. And then I'm going to solve from here. Okay, so minus 5 on both sides. And that's what makes this just super easy, is since these are basically identical left-sided equation, getting x by itself is going to be the same process throughout. So 2x equals 11 minus 5 is 6. 2x equals negative 16. From here we divide off 2. X is equal to a positive 3. X is equal to a negative 8. And then obviously we want to write our final solution in bracket notation. So -8, comma 3. And this would be my final answer for this portion. Does that kind of make sense? Okay. Let's go on to page 5. And actually, you will be working example 5 on your own. Discuss any different answers, or you need me to rework these, I'll be more than happy to. So far, are there any questions? I mean, this is pretty much solving absolute value equations. Should be very straightforward. Remember that you're going to have 2 solutions. We'll talk about special cases next class. But for right now, the homework problems that you have assigned tonight, all of them should have 2 answers or 2 solutions to your work. Any questions so far? Okay, so we're going to go on to inequalities here. Now, inequalities is going to be treated just a little bit different, okay? You're still going to think about units away from a certain point. However, the sign of your inequality is going to affect how you look at your number line, okay? So in this case, we want the values inside the bar, right? If we have 2 or -2, the absolute value of these needs to be less than 2. So we're thinking about 2 units away from 0. Now, I'm going to take my highlighter here because I'm going to kind of show you some things. If I am thinking about this region here, 2 units away from 0 in this direction, 2 units away from 0 in this direction. Since this is an inequality, let's talk about how we would write this in interval notation and how we would write each of those x terms in relation to their own inequality. So, if my reference point is 0 here, how would I represent this portion of the graph? How would I say that in words, I guess, as an inequality? X includes what values? Anything, what is this right here? Less than 2, right? So it represents anything less than 2, but what is this direction? Greater than -2. Very good. Now, this is just looking at it in terms of x. Let's think about interval notation. How would we write this in interval notation? Read the graph left from right. -2 is the first value we come to, comma, +2, close. So this is actually what my interval notation would be. But I want to point out some things on this, what we drew up here, in comparison to the original equation. Now, if you look at that, my absolute value is less than 2. Are the signs on both of these that we express the same? Are both of those less than signs? No. Which one represents the less than sign? The positive version, right? What happened when we made the relationship between the negative version and x? What is different about this sign than our original equation? Or, sorry, inequality. Is it in the same direction? No, it's what? Flip-flopped, right? Yeah. So if you look here, the positive version is the same. But what happens when we wrote the negative version? You flip the sign. Now this is going to be a trait that you will see that's consistent through all of these examples. I don't want you to just memorize, oh, I got to flip the sign, but please note that this is what's going to happen when we write our 2 inequalities, because we're going to solve them just like we did equations. One of the signs will be different depending on your original expression. Okay? And as we do some more examples, it'll kind of hopefully make sense. Now with all of these, you will need to graph. and you will need to write them in interval notation. Your homework does not require you to graph on some of them, but I put it in the notes specifically and on the wire that you must graph to get credit for any inequality. Okay, so let's look at number 6. We're going to solve this very similar to how we did equations. We're going to have the 2 different equations. However, as our last example we just saw, what do we need to do different when we are setting this portion equal to the negative version? You need to flip the sign. Very good. So, x minus 2, we're going to keep this sign the same because it's against the positive version. When we write our second inequality, we want to flip the sign, so now it's greater than or equal to the negative version of that number. Once again, we're not changing anything inside the absolute value, we're just changing the number on the outside. From here, we have our 2 expressions, inequalities. We want to go ahead and solve for x, so add 2, add 2. Keep in mind, I don't have any examples on here. What happens if we multiply or divide by a negative number in an inequality? You flip the sign. So pay attention to those. But this first one, you should get x is less than or equal to 5. Over here, you should get x is greater than or equal to negative 1. Now, I want to graph this real quick because inequalities in this section are either going to fall under the conjunction category or the disjunction. And basically the only way you're going to be able to figure that out is looking at how the graph is. So make sure you're plotting the right numbers. I want to shade x is greater than or equal to negative 1. So I'm going to have brackets on my negative 1. But I want to shade everything less than or equal to positive 5. So if this were my graph, think about our terms that we talked about at the beginning of class, conjunction and disjunction. Does this include all of the values in between, or does it include the values outside of it? In between, right? So would this be a representation of a conjunction, like an and statement, or a disjunction, an or statement? An and, very good. Okay, so this is a conjunction. I want to write my interval notation, reading my graph left to right. What's the first value I come to? Negative 1, comma 5. Very good. And so this is how I would answer this portion. Okay. Now, I want you to solve 7 by yourself. Okay, example 6 and 7 are very similar in format, so if you get stuck, refer back to 6, think about the different steps that we did. Okay, questions about example number 7? Makes sense? Do I need to leave it up a little bit longer? Only when you divide by a negative number. And so since, guys, Alexis asked a very good question. Both of these expressions right here, or equations, sorry, inequalities, we divided by a positive version of the 3. Guys, listen. If for some reason this 3 had been negative, yes, you would have flipped the sign. But if it's positive, you keep it the same. Okay, go over to example 8. Now, 8 is a little different. We're gonna use all the same principles, guys. However, the last couple of examples, we were dealing with values that were less than. Here, this is our first example that says the absolute value of x must be greater than 1. In math terms, what this translates is that x must be more than 1 unit away from 0. So we're going to treat this just a little bit different. if we're thinking about a number line, and this is 0, what would we shade to represent something that's more than 1 unit away from 0? Okay, we're not going to shade 0 to 1 because that represents 1 unit away from 0. We want something more than 1 unit away from 0. So we're going to start at our 1 value and shade everything to that right all the way up to positive infinity. Now, just like with anything that we've seen so far, these are pretty much mirror images, right? So if we're looking at this in the negative direction, we want to shade everything from -1 and over. Okay? So this is where it starts to transition and change. You've got to look at the sign and what it's actually saying. Now, let's take this graph and write not only our interval notation, but what values of x we have. Okay, so if I wanted to write this left side of the portion in terms of x, what would I write as an inequality? X right here represents everything, what? Less than -1, right? And this portion of the graph represents everything as far as x is what? Greater than 1, right? Perfect. Now, looking at the graph, what kind of graph is this? Is it conjunction or disjunction? It's disjunction. So we have that or statement. So x represents values that are either less than -1 or greater than 1. Let's think about our original equation. Which one of these, the positive or negative version, matches the sign from our original absolute value equation? The positive one, right? So it's consistent to say that whether the sign is less than or greater than, that positive version, we don't flip the sign. When we set it equal to the negative version, that's when you flip the sign. So just make note, you're going to flip the sign when you have a negative number, or when you set it equal to a negative number. Okay, last but not least on this problem, I do want to write this in interval notation properly. So since this is a disjunction, it's a union, we're going to start at negative infinity. We're going to go to -1. We're going to do the union in between because there's a break in my graph. +1, positive infinity, and so my final answer in interval notation would look like this. Okay, very, very good. Okay, example 9. We're going to do these two. We're going to do this example, and then I'm going to have you do 10, 11, and 12 all on your own. So example 9, we introduce a numerical factor into the absolute value bars. So what we want to do is set this portion against 3 and -3. We know that the first positive value, we keep the sign the same. When we write our second inequality, we flip the sign and set it against the negative version. Other than that, it's the only thing that's different from solving from equations. Add 1 to each side. X is greater than 4. X is less than -2. We do want to graph these. Just pick 2 points. We're going to shade everything that's less than -2 and everything greater than 4. And then we want to write our final answer in interval notation. So if this is a disjunction, how do we write it in interval notation?
-infinity, -2, and then union, and then 4, infinity.
Perfect. Perfect, perfect. Like I said, that's the nice thing about this section, guys, is that it's either going to be a union or a conjunction. or a disjunction and a conjunction, you should basically see those two graphs. Now, like I said, we'll talk about special cases next class. But for right now, your homework, I mean, it's either going to be a graph that looks like this or a graph where they're meeting in the middle. Okay? So what I want you to do is I want you to spend the next like 5-6 minutes going over example 10, 11, and 12. If you'll go ahead and look at 11 and 12, what do you need to do to both of these inequalities before you need to isolate the bars first, right? We need to get rid of that 4 by doing the opposite operation, and we need to get rid of the 2 by doing the opposite operation. So once you get to number 12, if you will, hold off, and then I will show you the answers to 10, 11, and 12.